Okay, everybody should be able to see the screen here. Everyone able to see the screen?
Yeah, we can see it.
Good. All right, so today's class, continuation from last time, we were going to finish up Module 0, which is a motivation and introduction to the emerging topics in solid-state electronics. So last time in class, we just gave a big overview of these things, and we got into the specifics about a few of them, and we're going to cover some of the rest today. So the thing that I want you to come up with, the take-home message for this module, is that semiconductors play a very important role in modern electronics and in our everyday life. And so it should give you a bit of a motivation to be able to understand how the fundamentals of semiconductors works, because they are the fundamentals of all these different types of devices, amazingly. And their use is only going to become more and more prevalent. And as you've seen from the videos, our little homework assignment on the global shortage of semiconductors in 2021, you can see that when we don't have semiconductors, we're in a lot of trouble. Last time in class, we talked about some of the roles in the area of digital electronics. We talked about Moore's law. Can anyone tell me what Moore's law is from last time? Quick review.
I believe it was I think originally it was every year the size of semiconductors shrink by half and the amount of, I guess, ability of them doubles.
Yeah, exactly. And ability, so if we get into the weeds of what Corey said about ability, there's two things that happens. When you shrink down the transistor, number one, you can fit more and more transistors in the same area, right? And having more transistors allows you to do more complex computations, because each transistor is a tiny computational element. Okay, it acts as a digital switch, and that's the basic building block of all these complex, what's called the arithmetic logic units, and which are, this parts of microprocessors. Okay, so that's one thing, more computation. The second thing, does anyone remember what the second thing was? The second advantage of shrinking down the transistor.
I believe it runs faster.
That's right. Exactly. Yeah. Thank you, Clayton. So they run faster. You're able to, specifically in electrical engineering terms, they have smaller capacitances so that you can turn them on and off faster. So you can turn your switch on and off faster. As a result of that, what happened is that the clock speeds went up. Okay, because the transistors are faster, we went from clock speeds that were 108 kilohertz, which is 0.1 megahertz. So 0.1 times 10 to the 6th. And now we are at the best performing processors are close to 4 gigahertz. That's 4 times 10 to the 9th. All right, so you think about the huge growth of that. Okay, so the miniaturization of transistors has been huge in the area of digital electronics. And last time in class, we also, touched on this idea that if we look at the 70 years of the transistor, we can trace some of the important events that happened there, and corresponding to the advancements of the transistor, there were corresponding advancements in the computing revolution, right? We went from transistors to integrated circuits, and once integrated circuits kind of came around, we saw the PC revolution in the 1980s to the 90s. We saw the mobile phone revolution starting in the 2000s till now, and then of course the internet revolution starting in the late 1990s till now. Now we are seeing the computing even going beyond this, and we've seen the growth of GPUs and their use in artificial intelligence and learning. So we are going to see some really interesting stuff going forward from the 2020s into the 2045s. And we're already seeing some hints of that right now. Okay, so this was about Moore's law. We talked about the miniaturization of the transistor and how this actually forced innovators to come up with new geometries of the transistor, going from the planar FET to the two-dimensional FET to now then into what's called the all-around nanosheet FET. So that was pretty interesting. And then on the memory side of things, so these transistors are used for computation, right? They're used for doing the compute, but also you use transistors or transistor-like structures, semiconductor structures, for data storage. We've gone from magnetic disks into solid-state drives, and we talked a little bit about last time about how there was a big advancement in creating three-dimensional memories, where you have memory layers stacked on top of each other, and that allowed you to greatly increase the storage capacities. That started about in the 2010s, and they've continued until now, led by Samsung, Toshiba, Micron, some of these other companies. Once they move to 3D NAND, now it's typical that we'll have 500 megabyte, 1 terabyte, 2 terabyte solid state disks, whereas before they were very, very expensive to do that. And all of our servers are really running on these solid state disks as well. Solid state disks are much more reliable. They're much faster than typical magnetic disks. And so that's also led the revolution in the mobile phones and things like that, because they're much more robust. Okay. Lastly, we ended up with the trends in digital computers going in the opposite directions. So there are some types of computer chips which are going to more and more transistors. In the case of the NVIDIA Volta GPU and the Cerebras wafer scale engine, going up to 1.2 trillion transistors for doing massive amounts of compute. And on the other end of things, we have the chips themselves becoming smaller because you're using fewer transistors. So these types of chips are designed for very specific applications in sensing. They're not doing massive amounts of compute, just enough to do sensing. And this area is kind of called smart dust, wireless low power sensors, nanosensors. We'll see more of that as the field of Internet of Things becomes much more important. Does anyone know what IoT is, by the way? You may have heard that buzzword. Okay, IoT is Internet of Things. This concept that we are going to have sensors in everything, like all part of our lives. You know, we get up in the morning, we have sensors on our toothbrush, we have sensors in our toasters, we have sensors in our cars, like, and they're all going to be networked through Wi-Fi or through Bluetooth or through 3G. Okay, and these network sensors are going to provide convenience to us. It'll provide things like infrastructure monitoring. If you imagine having a bunch of sensors on a bridge, infrastructure monitoring for things like that, for security purposes and so on. Okay, so today we'll start off with going into new areas of memory. This device is called the Memristor. Okay, and I'm bringing this up because this was a relatively new solid state device that kind of came about starting in about 2008, and it's become a area of intense research over the past 5 to 10 years or so. Actually, since 2008, since HP discovered it. Now, the context of this is we learn in this class, we focus on the diode and the MOSFET. Okay, that's really where we spend most of our emphasis on. We learn the fundamentals of solid state electronics. We learn the fundamentals of semiconductor physics, and that will allow you to understand new types of devices. This is an example of a new device that's coming out, and we expect more and more new devices to come out as we move forward. So that's why it's important that you understand the fundamentals of semiconductor physics. Okay, so a little bit of the story of the Memristor. Let's have a show of hands. Anyone have heard of the Memristor?
Yeah, they're used a lot in neural networks, AI neural networks, crossbars.
Crossbars, that's right, that's right. In fact, there's a company called Crossbar that made it famous. I'll talk about that on the next slide. Thank you, Melvin. So there's an interesting story behind the Memristor, is that this Memristor is this theoretical mystery, or it was a theoretical mystery passive circuit element that relates magnetic flux to charge in the same way the resistors relate voltage to current, and the same way that capacitors relate voltage to charge, the same way inductors relate flux to current. Okay, so that's a mouthful. So let's look at this graph here. Okay, and I want to start off in the area that hopefully some of us are familiar with. We'll start off with, when we think of electrical circuits, we think about the symbols and the circuit schematics, And there's three elements that we know well. Okay, the one that we know the best is the resistor. And the resistor has, it is governed by Ohm's law, V equals IR. Okay, and another form of Ohm's law is dV equals R dI. Okay, so essentially what the resistor is doing, if you want to think about it by this equation or think about it by Ohm's law, what it's doing, it's relating voltage to current. Okay, so you have your voltage here and your current here. So the resistor is in this part of this box. Okay. And by the way, this box was sort of made in, this was theorized by researchers at UC Berkeley way back in the day. The second most common electrical circuit element that you're hopefully familiar with is the capacitor. The capacitor relates charge to voltage. So you imagine current flowing in the capacitor here. The charge is stored on this device. Okay, and we'll go into some of the details of MOS capacitors later on in the term. So it's okay if you don't recall all of this right now. But the equation for the capacitor is Q equals CV. The charge is equal to the capacitance times the voltage. Now you see here that this is actually written in a differential form. So dQ is equal to C dV. Okay, but often like in classes, we teach Q equals CV. So the charge equals the capacitance times the voltage placed on the capacitor. All right, so this is relating voltage to charge. Then in this area of the map, the inductor relates magnetic flux to current. All right, so d phi is equal to L di. Now, the way to think about an inductor is that you think about an electromagnet. Okay, imagine that you have a coil of wire going like this. When you flow current through that coil of water, through that coil, a magnetic field is generated in the middle of this. So if you remember some electromagnet experiments from back in the day, if you've ever did experiments with that. And a practical example is the solenoid locks in the car are made with electromagnets. You just put a current through here, it creates a magnetic field, and the magnetic field pushes the door locks into position. All right, so all of that is done by a magnetic field. Magnetic field phi is equal to the inductance, which has to do with the number of loops there are here, times the current that you're putting through the wire. So these three, for many years, these three circuit elements were the go-to elements for electrical engineers. So if you look at it in this quadrant of the map, you can see magnetic flux and current. And so you have these three relationships here. They're all linear relationships. Voltage to current was the resistor, voltage to charge was the capacitor, and then magnetic flux to current was the inductor. So some researchers at Berkeley way back in the day theorized that, there must be, maybe there's another element, a mystery element, which fits in this box, which relates charge to magnetic flux. Okay, and they theorized that this element could be called the memristor. It relates magnetic flux at d phi equals the mem resistance times the charge. Okay, and the reason why people were excited about this, if such a device could be built, then it would be able to store information. Because this relates like magnetic flux to charge, it could store data, kind of like how capacitors are actually used to store data in random access memory. Okay, non-volatile memory. So it wasn't until 2008, a couple decades later, when this device was actually fabricated. And it turns out it was fabricated, it was realized using semiconductor technologies. So HP created this bi-level titanium dioxide thin film that had a doped and an undoped region. All right, so doped region and an undoped region like this. And so what was interesting with this device is that you could, by applying current through this device, you can see how it's connected in an electrical circuit here. The current goes through the device. You could actually change like doping or oxygen vacancies. We'll talk about that in detail more later, what those things are. But basically, you could change the properties of the material, and it would have a resistance, a certain type of resistance in one case if it was undoped, and a different resistance when it was doped. But you could modulate this, okay? And it turns out that this type of device could emulate the properties of a memristor. All right. We're going to be talking about doping, so we'll, don't worry if it all doesn't make sense yet. And this device has found some very interesting applications in ultra-high density storage, and as Melvin mentioned, AI, learning networks. So this was 2008. Not many years later, less than 10 years later, Crossbar, which is a company based in California, but a lot of the fundamental technologies was invented or developed by a professor, Wei Lu, who's at the University of Michigan in Ann Arbor, not too far away from here. He came and gave a talk at Wayne State once, and it was very, it's quite interesting. So they talked about this concept of resistive RAM, or RRAM. Okay, and if you Google this term, you'll find that it's quite an exciting new memory technology, new area for this AI computing, neuromorphic computing. Okay, we have a new faculty member in our department, Professor Goste Tutenkwaglu. That's kind of hard name to pronounce at the end, but like if any of you are interested in this area, she is an expert in materials for neuromorphic computing, and she spent many years at Microsoft Research. We're very happy to have her here in our department. So in a resistive RAM, you can store a data bit by pushing ion impurities into the switching medium using an electric field. So when we talk about data storage, the way that engineers will often think about data storage is that you have a material, okay, and you can make that material either a 1 or a 0. Okay, that is the fundamental building block of memory, is that you have some kind of way of storing a 1 or a 0 in the device. And if the device is non-volatile, meaning it works even when the power is off, it remembers when the power is off, then the material has to remember what state you put on it. A simple capacitor won't do that. You need something for non-volatile memory. You need something where the properties of the medium changes, and that way you can remember it. So like imagine like taking a magnet and flipping it from north to south to north. That's one way of storing data. But the way they do it in resistive RAM is that they actually flow a current from the top electrode to the bottom electrode, and they push ion impurities into the switching medium. So the switching medium is in between the top and bottom electrodes. So you drive a current through here, and you end up creating these ion impurities. If we get into the details of it, there's different ways it could be done, including like something called oxygen vacancies, but it switches the properties of the medium. So the resistance changes, okay? So if you were to now measure the resistance between the top and the bottom electrode with these ion impurities in there, you'll see that the resistance has changed. So this is a memory storage element. Now, the nice thing about this is that this is extremely scalable, okay? Scalable because it can be stacked in 3 dimensions. So the way that crossbar memory works is that you have a set of horizontal top electrodes, and then you have a set of horizontal going, let's say, north-south. You can see these gray ones here. Imagine these are going like north-south, and then these gold ones here are going east-west. In between them in blue is the switching medium. All right. So you can make these two-dimensional grids. Just ignore the rest of this for now. Like just think about this in 2D, that you can create everywhere where the top gray bar meets the bottom yellow bar, the gold bar, you can have a little bit of the switching medium. And in that switching medium, you can store 1 bit of information. So the reason they call this a crossbar is because you have the bars going east-west here and then north-south here. And so you can create memory in a two-dimensional grid. Okay, so you have the bits being stored in a two-dimensional area. Now, the nice thing, as I mentioned, is that you can turn this into 3D by just stacking them on top of each other like this, multiple layers. Okay, so you can increase the capacity of the memory just by building more layers upwards. It's a very, very cool, scalable concept. All right, so they demonstrated, this is from a few years ago. I think they've come even further since then, but they're demonstrating a low latency, low density memory, and then high performance, high density memory. These types of memories, they haven't completely replaced standard memory yet, the standard semiconductor memory yet, but they have some advantages in neuromorphic computing because I don't know if you've heard about this concept of like neural nets, and you use GPUs to train neural networks. So these are the things that Google and Facebook are doing to do like facial recognition and things like that. So if using this kind of memory, it turns out that doing AI learning is much more memory efficient than the standard way of doing things using the GPUs. So one of the issues currently with AI and machine learning is that it takes an incredibly large amount of computing power to remember complex things. So Google and Facebook's data servers are consuming gigawatts of electricity in their learning networks. And these types of approaches, which don't use GPUs, which actually store the neural nets directly in the material rather than by doing matrix computations, it saves a lot of power. Okay, so that's why this stuff is very exciting. I know I kind of glossed over a lot of the details. It's intentional. We could spend hours talking about how those things work. But I just want to give you some exposure to that. Any questions here? On resistive RAM. Okay. For the chemical engineers in this class and the material scientists, this area I think will be quite interesting. Quite interesting for you in your careers to see how this area develops, because this is essentially you're changing the material properties. This is a material science and chemistry type thing where you're creating these vacancies. It's almost like electrochemistry, but using electrochemistry to store data. Very, very cool. Okay. So the next area, if we can back up here for a second, just for context. So we talked about data storage and memory, memristors and RRAM. Now we're going to jump over to here on the power end of things, photovoltaics. Okay, we're going to focus a little bit on that because that is a very important application now for sustainability. All right, so most of you know that photovoltaics or solar cells, just another word for solar cells, they convert solar energy to electricity, and they do so by generating charge carriers in a semiconductor. We will go into the details of that later, but I just want to mention what the brief concept is that when sunlight, imagine I have a semiconductor material here, when sunlight hits the semiconductor material, it creates what's called an electron-hole pair. An electron and hole are created. The electron has negative charge and the hole has positive charge. It turns out that with the photovoltaic, a solar cell, when the electron and hole is created, they actually end up moving in opposite directions. So the electron moving one way creates some current. The hole moving the other way creates more current. And so the currents actually kind of add up. This is very different than other ways of, generating electricity. We think about, the way that we've been doing it for centuries is we use turbines. And turbines use something called Faraday's law to generate electricity through like a rotating turbine, and there's a rotating magnetic field. And this creates something called an electromotive force, and ultimately that translates into power. That concept we talk about in electromagnetics. The electromagnetics course, ECE 4800. You can also, of course, learn about it online. So one of the advantages of photovoltaics, of course, is that it requires no moving parts. Right? No turbines. It doesn't require a massive like Hoover Dam or something like that. It just requires sunlight. All right, just a material that like literally just produces electricity when sun shines on it. It's just amazing. We wouldn't have this without semiconductors. Solar energy is a great source of power because on a bright sunny day, the sun provides 1,000 watts per meter squared. That's a lot. 1 kilowatt for every meter squared of area in a desert, let's say. That's here on Earth. In Mars, that's obviously a lot less. Venus and Mercury, that's going to be more. Now, if you look at this is a nice little chart here. This shows the different wavelengths coming into the Earth's atmosphere. So you can see this says terrestrial radiation here. So there's a lot of light energy that's coming in on the visible portion of the spectrum, the stuff you learned as Roy G. Biv, red, all the visible colors. So fortunately, most of the light that comes into the Earth's atmosphere is in the visible portion of the spectrum, and this allows us to see things. And our eyes have evolved to see in the visible portion of the spectrum between 400 and 800 nanometers. There's also a lot of energy that comes in on the 800 nanometer to 2000 nanometers. This is infrared radiation. This is what's often felt as heat. And then below 400 nanometers is the ultraviolet region. So there's some ultraviolet radiation that comes through. Most of it is absorbed by our atmosphere. This type of radiation, as you know, is a little bit, it's more hazardous to us because it affects our DNA, which is used to encode our protein expression and things like that. That's a biology concept. The point is, like, we get a lot of solar energy on the Earth, and so I don't have the history of this off the top of my head, but solar cells have been around for many decades right now. But what's happened in the last, I would say, 10 to 20 years or so is that the cost of photovoltaics has come down, and so it's become a lot more feasible, economically feasible, to do a lot more solar power. This has come, kind of based on economies of scale. A lot of governments have invested a lot of money in order to produce manufacturing facilities for solar. Actually, a lot of the solar is produced in China, so they've invested a lot in making solar cells relatively affordable. But there's other parts of the world that are producing it too, including here in the U.S. The other portion of it is that governments and companies have made significant investments to switch to solar power. Okay, so you can see some examples of that here. This is an example from 2004. This is a 10 megawatt solar farm that was installed in Bavaria. That's in Germany. They're one of the leaders in solar power. So basically a solar farm, I think you've seen them here as well, basically a farm field where you just have a whole bunch of solar panels. And this example was enough to power 9,000 homes. Now what we're seeing in the US and in other countries, we are seeing building integrated photovoltaics. You can see this here, where there are solar panels built into the walls of buildings. I think that's pretty exciting. And how many of you have heard of this? How many of you have heard of solar solar roof tiles?
I've heard of
Alvin,
it.
you have? Clayton? Does anyone own it by chance? I don't. They're still a bit expensive. They're quite popular in California. And basically these are solar panels that you put on your roof and they look like shingles. I believe the return on investment for these things, if you live in a sunny area like California or Arizona, the amount of electricity produced by these panels will basically pay for the cost of the panel, I believe, in about 7 years. That's not bad. You know, you just have to put some money up front, and then you'll start to get free electricity, and over 7 years, the cost that you've saved in electricity will pay for the cost of the tiles. There are even some. Go ahead. Was it Melvin? You had a question there or comment?
Sorry. Yeah, more so a
please.
comment.
Yeah.
How do they? I mean, I know shingles are. If you have a lot of shingles, it's kind of heavy, but I would imagine these solar cells would be heavier than a shingle. And if a home was originally designed to hold up shingles and its structure was designed to hold up shingles, I wonder if there's any sort of structural ramifications to replacing shingles, traditional shingles, with these solar panels, or are they just light enough to the point to where it doesn't really make a difference?
Okay. That's a great question, Melvin. I probably don't know the detailed answer to that, but let me just mention what I do know. Is that, silicon. Okay, so I just mentioned that photovoltaics, solar cells, are made primarily from silicon, which is a semiconducting material. And silicon is made from silica, which is sand. Okay. So if you figure like the density of sand, the density of silicon will probably be similar to the density of sand. I don't imagine these things being much heavier than.
I see.
Much heavier than, like, traditional, especially if you had like, the more like durable type solar panels. Yeah. But fair question. I think that the roofs can handle the weight of those. What's interesting is that they have managed, companies like Tesla have managed to make some of these silicon solar cells look very much like shingles. And that's the thing. I don't know how exactly they do that, but it's quite impressive, quite interesting. And so, there are houses that are off the grid that just use solar power, and they have batteries in their garage, like these big battery walls that store the power, so that when the sunlight goes out, you can rely on battery power, and when the sunlight comes back, it just charges the battery. So you kind of need both of those things. If you want solar to be your primary source of energy, you also need to have storage. Okay, so photovoltaics and wind power, they're expected to produce a significant fraction of the world's power by 2050. Japan expects 20% of power to be renewable from renewable sources by 2020. Recently, I think that the US was pledging to go primarily renewable by about 2040 or 2050 timeframe. So, this need for semiconductor-based photovoltaics will play a very important role in this. So last year, I looked at a future roadmap for some of these semiconductor technologies, and one of the student groups actually contributed to it as well. You can click on this in your class notes to find the actual article. Remember, you actually have to do this from campus or from VPN if you want to access some of the journal articles that Wayne State has access to through the libraries. You will not be able to access this at home unless you go through the VPN or through the proxy. If anyone has questions about that, happy to help answer that. So some of the key points from that paper that came out last year is that cadmium telluride is becoming competitive with silicon. And the way they denote how competitive something is that they talk about cost per kilowatt hour, or costs per watt, as you see here. Okay. In order for a renewable technology to be feasible, the economies of scale have to be there. Like the cost per watt, for example, if you have a coal plant, there's a certain amount of money that it costs to run a coal plant and generate 1 watt of power. Okay, so you can figure out what that cost is. Now, before, coal was much cheaper than solar, much cheaper than wind. But what's happened over the years through a lot of investments that have been made now, wind and solar have really caught up, and in some cases even surpassed coal, which is good because coal is also very highly polluting. So new materials, though, almost all the stuff we've done thus far has been with silicon, because silicon is relatively inexpensive, but cadmium telluride is becoming competitive, and its cadmium telluride has some more better efficiency than silicon does. There's a group of materials called 3-5 materials that have efficiencies up to 29% with single junctions and 47% for multi-junctions. Whereas typical solar cells are somewhere between 10 and mid-20s in terms of efficiency. That means like 20% efficiency means like, a 0.2, 20% of the sunlight that hits the solar panel is converted into electricity. The rest is either lost, goes through the solar panel, or is converted to heat. Okay, so again, this number here, a bright sunny day, the sun provides 1,000 watts per meter squared. If we had efficient devices that could capture 100% of that, I mean, that would be tremendous for our, this whole problem of the climate change. So scientists are working to get that number up. All right, and they're working on new materials that are expensive now, but if they turned out to be very efficient, they could really change the game in photovoltaics. You see single junctions and multi-junctions. The reason you have multi-junctions is that if the light from the sun can pass through one of the junctions, and if it passes through one and then it hits the next one, then you see how having multiple junctions can increase the efficiency of the solar cell. So if one junction didn't create the electron hole pair, maybe the next junction does. And some of the other things that are happening more on the logistics and manufacturing side is that you're starting to see building integrated photovoltaics, where you have like skyscrapers and condos and apartment buildings having photovoltaics built in. Flexible photovoltaics that can bend around objects. And that's kind of what allows things like Tesla to make these curved shingles for the roofs. And then, of course, most important thing probably is how to lower manufacturing costs. Okay, so that's sort of the roadmap of some of the things that you'll see in photovoltaics over the next 10 years. And I imagine that if the adoption continues, we are going to have solar power everywhere. We're going to have battery powered things everywhere. We're going to have electric vehicles everywhere, in a decade or so. Any questions on photovoltaics? Corey.
Yeah, I have a question.
Sure.
I guess, so you mentioned these Tesla zonal roof tiles, and that you get a return on investment after 7 years. Does the efficiency of those tiles?
Let me fix that. It should be solar.
Oh, is it solar? Oh,
yeah, sorry
awesome.
about that. It's zonal is my wife's name, and I think somehow is autocorrected.
Oh, gotcha. So does efficiency end up kind of start to like diminish over time? I know UV radiation can be very detrimental to materials and stuff. Not sure about the silicones and everything, but I mean, yeah, over time, I guess, does that affect the efficiency of the photovoltaic cells?
That's a good question. I believe that the efficiency of traditional solar cells made out of basic silicon, single crystal silicon, those have a they're pretty robust. Some of the newer kinds, like the things that are flexible photovoltaics and the photovoltaics that are made using printing technologies like inkjet printing, some of these newer areas, those are less robust, and they semiconductors made from polymers, for example, those things would become less efficient over time due to degradation from UV radiation, as you pointed out.
Okay.
But just a case in point, think about this: the Voyager spacecraft. Okay, it was launched in 1970. It was launched into space where there's massive amounts of radiation, and the Voyager spacecraft, the photovoltaic cells and those things have been ticking for the last 40 years. I think we're still getting signals from Voyager, and it's past the edge of our solar system now. It's amazing. Yeah.
Okay. Yeah, that's a good point.
All right. So now, again, for context, let's just jump back to this slide here. So now we're going to talk a little bit about the sensor side of things. Okay, we'll talk about cameras and imaging technologies. I think that's probably the most important one. So we're not going to go into the details of all of these, but we'll just touch on this most important point here. So jumping ahead then, semiconductor imaging technologies. There we go. Now, I just want to point out that this nice little infographic that you see here is focused on medical imaging sensors, medical cameras, right? But, I think it traces some of the important things, the important advancements that's applicable to standard cameras as well. So what are we talking about here? Semiconductors are used in digital cameras. Digital cameras are made primarily from silicon. Semiconductor light sensors, i.e. cameras, they convert light into electronic signals, and those electronic signals are stored on your semiconductor hard disks and in an image form, your JPEG images, what other formats they have right now. And what's happened over, I would say, the last couple of decades is that the imaging sensors and software that support that, they've become better. They've become better so that you can get really high quality images with these really tiny sensors. So case in point is the iPhone 11 camera that Apple makes. I mean, I think that Apple's real claim to fame with the reason why their phones are so expensive, yet people want to buy them, is just the quality of the cameras. So, you can see that the more recent cameras have multiple cameras on them, and they sort of combine the information from multiple cameras to do things like 3D imaging, depth sensing, perception, augmented reality, and things like that. But ultimately, these things are these tiny chips. I'm going to circle it right here. A tiny chip that looks like this. It's a CMOS sensor, and it's a bunch of pixels. Pixels means it's a grid. It's a two-dimensional grid. And in that two-dimensional grid, on that two-dimensional grid, there are pixels. And each one of these pixels is a light sensor. Now, I mentioned with the photovoltaics is that when light hits the semiconductor, it creates an electron-hole pair. So it creates two types of charges. And so what a digital camera does is that it stores those charges. And depending on how many charges are created in a certain amount of time, it will determine a grayscale level. Okay, so let's say within a certain amount of time you generate 10,000 charges. Maybe it'll give you a grayscale value of 200, and if you generate 5,000, then it'll generate a grayscale value of 100 instead of 200. So it translates the charges that are produced by light hitting the sensor into a number, right? And you have millions of pixels on one of these sensors. I think the iPhone 11 camera has, I don't know, maybe someone in the class can tell me. I know it's over 10 megapixel. Is it maybe 20? I don't know off the top of my head. The point is there's a huge number of pixels. Because we're able to make the pixels very small, let's say a micron or so, then we're able to pack many, many pixels on a chip. Now, someone in the class, maybe tell me, why would it be nice to have many pixels?
Does it make the photo like more detailed and more clear?
Yeah, exactly. It'll make the photo more sharp, more detailed. Exactly. You can capture more features on it. Yep, Corey mentioned better resolution. Thank you, Corey. So that's been kind of like a trend that's been happening in cameras over the last 20 years is more and more megapixels. You get more and more detailed images. Now, the other thing that's happened, especially in the last 5 years or so, is that the software on the cameras have gotten better at noise reduction. And that makes the low light imaging much better. We're able to take pictures at night now with cell phone cameras and they actually turn out okay. Now, I'll just put in a little bit of a note here. I think you'll find this interesting. With Moore's law, miniaturizing transistors for computation was great because it was kind of a win-win situation because you miniaturize, you're able to fit more of them in an area and you improve the speed of them. So it's great, win-win situation. But with digital cameras, you make the pixels smaller and smaller. It turns out the noise performance gets worse. So you gain resolution, but you lose, you lose some of the imaging capabilities or noise performance. So but they've managed to use like software methods to kind of deal with that a little bit more. But what you will notice is that, in an iPhone camera, if I'm just circling this, can everyone see my mouse, by the way?
Yeah.
Yes.
Okay, so you've all seen these cameras, so you know how big the chip behind here is actually not much bigger than the lens that you see on top of it, right? So it's about this big. Now, so these cameras have a certain cost associated with them. Does anyone know, just trivia, how much do these cameras cost? How much do you think Apple pays for these things?
A couple bucks or something, I don't know.
Yeah, just a couple bucks. But they sell it to you for 800, 900. So, but obviously Apple puts a lot of software into it. But the reason I brought up the cost of it is just so you can see that the cost of these chips has really, really come down. We are able to do very, very detailed resolution imaging for basically dirt cheap because of semiconductor technology and where it's come. Now, one of the things you might notice is if some of you have purchased or looked at DSLR cameras, digital SLR cameras, they are much more expensive. Those cameras can be $1,000 to $2,000, and they don't have all the other stuff that an iPhone has. The reason for that is because those sensors are actually much larger. The sensor for a typical DSLR camera might be about this big, where I'm circling with my mouse right now. Okay, now those DSLR cameras, because they have more real estate, they're able to either fit more pixels or make the pixels larger. Larger pixels will have better noise performance and they'll do better in dark light situations. All right, so there's been this sort of economy that's built up around the CMOS imaging chips. The small chips are cheaper. You can fit them into cameras and things like that, and fit them into like cell phones. The larger chips are used in DSLR cameras, so for wedding photography or professional photography, and also for scientific imaging, the types of imagers that go on the Hubble Space Telescope, for example. All right, so this little map here, I think it sort of traces the development of semiconductors and the role of semiconductors in imaging technologies. So if you just kind of like look historically back at 1895, this was a famous image of an X-ray. I wish I remembered the name of the scientist who invented the X-ray, but the story was that he took an X-ray on himself, and then he also took an X-ray on his wife. And this was a famous X-ray where the hand shows a wedding ring on it, because the wedding ring blocks the X-rays, but you can see the bones very well. So, X-ray technology was around for imaging inside the body, for imaging surfaces and imaging in general, like PMT tubes were used a lot for doing sensitive imaging for biochemical assays. Starting in the 1980s, actually the 70s and in the 80s, there was these things called CCD sensors, which were made using I guess you could say a precursor to some semiconductor technologies. And the CMOS sensor is the one that has become quite popular now. It's been used since the mid 90s in scientific imaging and medical imaging. They work, pretty much the same way that the iPhone 11 cameras work. They've just gotten like, good noise performance. They used to have the noise performance of CMOS used to be a lot worse than CCD. But CMOS was cheaper, so they'd be used in lower importance applications. But now the performance of CMOS has improved quite a bit, where CCDs are kind of starting to becoming obsolete. Now, where are we nowadays? We are in, there are newer types of imaging technologies that are coming about, in particular, like some flexible technologies, not only for sensing light, but also like producing it. There are, other types of imaging technologies which are not quite related to semiconductors, like ultrasound sensors that are becoming more portable, so that you can have ultrasound on your phones. Okay, this is kind of an aside. It's not really related to semiconductors that much, but I think the CMOS sensor, I think, is really what has reduced the cost of a lot of these things. One example that you can see here is a tiny camera endoscope. Because we can make our CMOS imaging chips really small, we can have these little tubes, these little like tubes with cameras on the end of them that you can like shove into parts of the body for different types of surgical procedures, or colonoscopies, endoscopies, and things like that. You can even buy these things. If you look on Amazon, you can buy like little endoscopes to put in your ear if you're looking for ear infections and whatnot. So it's made a lot of, I guess, a lot of biomedical imaging type things more portable, more available to the general public. So, future of imaging technologies, we're obviously going to continue to see use in the consumer electronics sector with smartphones. Medical, I mentioned some examples here, and we're going to see a lot in automotive. I think many of you, if you own a more recent car, you probably have cameras, rear view cameras, maybe lane guidance cameras in your cars. This is going to be a very large market for semiconductor cameras as we move more and more towards autonomous driving. All right, so now we're moving on to display technologies. So if we go back to our intro slide here, we are moving now towards this area. All right, semiconductors can actually be used to produce light and produce displays. So I think some of you may know, some of you may not. Oh, let's turn that off. Okay, sorry about that. Okay. How many of you have heard of AMOLED displays? Or maybe you've seen some of these types of technologies, OLED, the foldable phones that are coming out now. Does anyone own one of those foldable surfaces or foldable phones? Not yet. I don't. They're pretty expensive right now, but it's cool. Like when I first started teaching this class, I sometimes show a picture that looked like this and said, hey guys, you know what? In the future, we're going to see like flexible displays where you can actually bend a display like this. And this was some of the early work being done by Universal Display Corporation in 2010. And now it's just amazing. Like, 6 years later, Samsung released a curved UHD TV. Now we're seeing things like from Samsung and TCL. We are seeing like phones that are foldable. I mean, it's just incredible. So where is this coming from? Well, it turns out that semiconductor technologies, again, are responsible for this revolution. There's something, a type of semiconductor device called an LED, a light emitting diode. Okay, just like semiconductors can be used to detect light coming from the sun, semiconductors can also be used to generate light. There are certain types of semiconductors called direct bandgap semiconductors. And when you run a current through them, when you run a current through a semiconductor diode, we will talk a lot about what diodes are. This type of diode is that you can create light when you pass current through the diode. Turns out this is very efficient. I'll talk about more about that on the next slide. On this slide, I just want to mention that there's a certain type of LED, organic LEDs, that are that can be printed using, like, literally like inkjet printing techniques. And and in addition to other like semiconductor manufacturing techniques. But these layers that they build are so thin that they could actually be, they're thin enough where you can bend it and it's still okay. So what does an organic LED do? Well, you remember how I mentioned that a CMOS sensor is like a grid, a 2x2 grid of pixels, and each pixel is sensing the light coming into it? Well, a semiconductor display has a 2x2 grid of LEDs. Imagine a two-dimensional grid, and each pixel in the grid is producing light of different colors. So typical displays, as you know now, the 4K displays, they actually have, if you do the calculation, it comes out to 2 megapixels, so 2 million pixels. All right, so 2 million sources of light in a typical UHD display. All right, and as I mentioned, if they're made with some of these fancy organic LED materials, they can also be made into like a flexible display and made relatively inexpensively. So that's one of the reasons we've seen the cost of TVs, some of these 4K TVs, come down from, multiple thousands of dollars to now just, you could buy it at Costco for like $300 or $400. So where's the future of display technologies? We are going to see more and more curved displays. We see a foldable phone here, bendable phones. We'll see bendable laptops. We're already starting to see curved wearables. So wearable devices, smartwatches, different things that you might have for physiological sensing. Being able to make electronics curved is really nice because it conforms to the shapes of the human body. So there's a big advantage of being able to make these types of display technologies in bendable materials. So if you imagine like a watch, for example, if you could make displays that go around your entire wrist, that might be pretty nice. All right, Melvin, question.
Yeah, so I was curious because this is actually pretty interesting. What's the feasibility of something like electronic paper? I'm not even sure, something like that,
Electronic paper, like that's sort of where this type of technology is going, actually.
Yeah, this one here, it seems like it, yeah.
Yeah. So e-paper is actually somewhat of a different technology than OLEDs are. In an OLED display, each pixel is actually producing light. And in an e-ink display, you actually have literally colored liquid, small amounts of colored liquid that's going into the different pixels. And that colored liquid is what gives it the appearance.
Yes, I see.
So like, give you an example, like an OLED display would be something that's like in your tablet, like your Samsung or your iPad tablet. Whereas an e-ink display would be something that's on a Kindle.
Yeah.
And the Kindles, they do use semiconductors to basically direct where those which parts become transparent and which parts become light and which parts become dark. But those things are not emitting light. That's the difference. The e-ink displays, like they're not really emitting light. They're only blocking light in certain places.
I see. I see.
Yeah. Great question, though.
Thank you.
Okay, let's continue then on to solid state lighting. This, I would say, is almost becoming obsolete right now because, you know, in the next 5 years, probably most people won't even remember what an incandescent bulb is. How many of you know what an incandescent bulb is? Just show of hands. Okay, Corey knows. Bob, Prakash, Melvin, Jinan, Clayton. Okay, so maybe more than half of you know. The incandescent bulb is what was invented by Thomas Edison. Okay, and we use that for a very long, you know, many years. At the time I made this slide, and I think this is still true, is that about 1/3 of the US's electricity consumption is for lighting. And an even larger part is for heating, but that's a different story. 1/3 of it is for lighting. And of course, if you use more energy efficient light bulbs, that can reduce our energy footprint greatly. And so by moving to solid state lighting, which are LEDs, they use 66% less power compared to incandescents, and that results in 10% savings in the energy usage. And that's quite a huge amount. Okay. So where did semiconductors play a role here? We could talk a little bit about how solid state lighting works. The incandescent bulb, one that you see here, essentially what happens in this bulb is that you have this glass cavity, and that glass cavity is full of, you know, there's nothing in it. It's vacuum, actually. The air has even been pulled out of it. There's a little filament in the middle here like this, a little wire, and you've seen those wires, I'm sure. When you run current through that wire, the wire gets hot and it emits light. So that light emission happens through a process called thermionic emission. It can produce a lot of light, but the disadvantage is that it's only 10% efficient. So 10% efficient means that 10% of the electric power that you put in is converted to light. What is the rest of that power converted to? Can anyone tell me?
Is it heat?
It's heat. That's right. 90% of the power that you put into it is converted to heat. And that's, you know, that's some of the best that we can do with thermionic emission. About the, you know, around the 2010 timeframe, the fluorescent bulbs were becoming very popular, and in fact they are still reasonably popular right now. They're used in a lot of industrial type scale. The way the fluorescent light bulb works is, again, you have a tube. Well, you don't have like a bulb, but you have like this kind of tube-like thing, and inside this tube you have a gas. And when you put a current through this bulb, that gas lights up. Okay, it's like an electrical discharge. That discharge is absorbed on the walls of the fluorescent bulb, because the walls have these things called phosphors on them. There's ultraviolet light generated inside the fluorescent bulb. The phosphors absorb the light, and then the phosphors put out their own light, and that light is in the visible spectrum. If you go to a tanning salon, then like they have bulbs, like fluorescent bulbs, that don't have the phosphors on them, so they just radiate out ultraviolet radiation, ultraviolet light everywhere, and that's how you get a tan and skin cancer. Fluorescent bulbs are 30% efficient. They're 3 times better than incandescent bulbs. So there was, in the mid 2000s, there's you know, many people started using these. The incandescents started to get phased out. But the LED lighting now is even better. It can be up to 65% efficient. The way the LED lighting works is the same principle of an LED that I mentioned on a previous slide. A light emitting diode is a semiconductor component. It consists of a p-type semiconductor and an n-type semiconductor that are sort of very close next to each other. And when you flow current from the p side to the n side, some of that energy is converted into light. Okay, in fact, like up to 65% of it can be converted into light. And the rest, of course, is converted to heat. So I've been impressed that over the last 10 years that we really have rapidly adopted LEDs. Now, if you go to Home Depot, pretty much LED bulbs is what you're going to find on the shelves. So I never imagined that the adoption would be that quick, but it's been quite amazing. So LEDs are made out of semiconductors, typically like different types of what's called 3-5 semiconductors, not silicon, because in order for LEDs to work, you need something called a direct bandgap semiconductor. Whereas silicon is an indirect bandgap semiconductor, some of these 3-5 semiconductors are direct bandgap, and that's what allows them to emit light when you run current through it. Okay. And just a little bit of trivia over on the right side here. 2017, this is an image of Detroit. And Detroit was actually the largest city at the time that was lit entirely by LED lights, 65,000 of them. Okay, before 2017 and the 2015-2014 timeframe, you might remember that some of the neighborhoods, some of the areas of Detroit had really poor lighting and these really ugly like gas lamps that were like this ugly yellow color. You know, you could see them driving down I-75. My wife and I lived in Detroit at the time, like in 2017. We lived right on Woodward, and there was one night literally where we saw Woodward light up, and I'm saying it literally lit up like all the way from Midtown down to downtown. And because that was the mayor at the time, you know, he was planning this out, and he said like, "Oh, switch on the lights," and they just all came on. It was amazing. I mean, it really transformed the whole like Woodward corridor. So I think since then they've had some problems with some of the reliability of the types of LED lights they purchased. But in general, like LED lighting is quite very energy efficient and extremely reliable. Whereas, you know, an incandescent bulb, because it's generating so much heat, the heat will basically wear out the element over time. But LED lighting being much more efficient, I mean, it can last hundreds of thousands of hours. It's quite, you know, quite reliable. So that's why, you know, cities like Detroit, you know, cities all over the world now use LED lighting, and that trend will likely continue, I think, to the point where most cities will be using LED lighting. It makes sense. This is a really cool picture of Detroit from the, I believe it was from the space station. And then I think some more recently in the last few years, I think the smart home stuff is becoming really popular. You know, it's been around for more than 5 years, but I think it's sort of gained more steam now in the consumer sector. So you know, companies like Philips makes this thing called Hue, where you can, you know, put LED lights in your home and control them with your smartphone. You can control the lights coming out. And the advancement that happened there is that the cost of RGB LEDs became a lot less expensive. So there are certain types of LEDs that just produced white light, but nowadays, like you can get LEDs that produce red light, green light, and blue light. And so it's actually putting out 3 colors in different ratios. And just through your smartphone app, you can tell the light bulb like what ratio of red and green and blue to put, and you can basically get almost any color in the spectrum, depending on what your mood happens to be. For example, in certain types of blue heavy light is kind of good in the morning, so it kind of creates alertness. Whereas at night, you do not want to use blue light. Blue light will actually, it stimulates the cone receptors in your eyes, and it actually keeps you up at night. I don't know if some of you have these like light filters on your phones or computers when you're going to sleep at night. At nighttime, you don't want to use they're basically blue light filters. They eliminate all the blue light coming from your phones and your computer screens, because if you look at blue light like within a few hours, within an hour of sleeping, it will make your sleep less efficient, and it might actually create insomnia. So keep that in mind. I always use the light filters on my computer. What else can we say about LED lighting? I think that's pretty good. So let's continue here. Autonomous and connected vehicles. We have about a half an hour left, so I just want to make sure we get through the rest of the material in today's class. Let's see, we have, yeah, 1, 2, 3, 4, 5, 6, 7. Yeah, I think we can get through here. So this area, autonomous and connected vehicles, I think this is, of course, very important to us being in Detroit. Semiconductors are already playing a massive role in these areas. I mentioned that little anecdote that we had. Ford is a part of our industrial advisory board here at Wayne State, and one of our board members actually said that Ford is going to be hiring mostly electrical engineers going forward, just because there's so many electronics in the car, and all the electronics really are made from semiconductor components. So we just look at like some of the different components in an autonomous car. Now, this focuses on autonomous vehicles, but if you think about already what's in your car, we mentioned cameras, we mentioned digital electronics and computation. We mentioned things like GPUs, which are used for image processing. Well, that's in autonomous vehicles. Displays, like LCD screens, your infotainment screens on your displays, those are all semiconductors. The cameras, engine control units, different types of sensors, light sensors, they're all semiconductor components. And that is why that, this whole semiconductor shortage has made it so difficult on the automotive industry in the last year or two. So something specific to autonomous cars, many of you know a lot of these concepts already, but there's just a ton of sensors on a car and a ton of compute on a car. So things like, you have GPS sensors, so semiconductors here are used in a lot of the wireless components, the wireless radios that are used for GPS. The LiDAR is something where you have a laser light that's rotating around. LiDAR, now we have semiconductor lasers that are an important part of LiDAR. We have lasers in all sorts of different parts of the spectrum that used to be very expensive, but now because you can make them using semiconductors, they become a lot cheaper. Video cameras, I mentioned digital cameras are based on semiconductors. These types of radar sensors, actually a lot of the radar sensors might be based on ultrasonic, and that's not quite semiconductor, but the underlying computation circuitry that processes the data are made from semiconductors. And of course, the main thing here is that you have a central computer, right? The main brains of your car is all like quite a powerful digital computer. Stores all the information, manipulates steering, the accelerators and the brakes, has a lot of like software on it, and so on. So where this field is going is, Elon Musk said recently that he wants to move away from LiDAR because LiDAR is very expensive, and he wants to use video cameras exclusively. One of the downsides of video cameras is that video cameras can't do depth perception like LiDAR can right out of the box. LiDAR can sense the distance. It does time of flight measurements and senses the distance between the LiDAR box and what's in front of you. So it can generate a three-dimensional point cloud of all the objects around you. Elon Musk is saying like the video cameras are a lot cheaper. And if you have multiple video cameras that are doing like stereoscopic imaging, like looking at things with two cameras can allow you to see in 3D, just like our eyeballs can see in 3D because we have two of them. So using video cameras and using like high performance processors and GPUs will be able to do this three-dimensional imaging that's required for autonomous vehicles. And then you need all the AI stuff in order to detect or recognize things. Is it a person? Is it a stop sign? Is it a lane? Where do I need to turn? All that sort of intelligence that autonomous cars do right now is all, a lot of compute done in GPU units, again, made in silicon. So a bunch of sensors, there's lasers, imaging cameras, wireless communication, all semiconductors involved there. This was kind of interesting plot. Like if you look at from 2014 to 2015, just a year, but Google's autonomous vehicles like went from 500 miles per disengage up to nearly 5,000. So it's a 10x improvement. Miles per disengage basically is like, or someone's sitting in the car and they're basically like measuring, well, how many miles can you go before something goes wrong in the autonomous thing and the human driver has to take over. And this obviously has gotten like much better than this. Like there are Tesla vehicles on the road right now which are doing tens of thousands of miles, if not hundreds of thousands of miles, you know, totally autonomous. It's quite amazing. So I mentioned LiDAR. LiDAR has been something where it is a pretty expensive component. This is like one company that's trying to use silicon, doing a lot of things in silicon semiconductors to reduce the cost of LiDAR. Typically, you know, when you do when you try to make lasers out of materials that are not silicon, they tend to be very expensive. So the cost here is high. But when you do the same type of things using silicon photonics, you can you know, drastically reduce the cost. And what does silicon photonics actually mean? They actually take this semiconductor material and they build lasers, modulators, detectors, optics, all sorts of components just on the same chip. This is sort of like talking not just about semiconductor technology, but also what's called MEMS technology. Okay, I'm not spending too much time on this because just in the interest of time here. But LiDAR obviously is very important for level 4 and level 5 autonomous vehicles. And they do a lot better than the sonar type things, which are based on ultrasonics or sound. All right, so now let's switch gears a little bit and talk about another area of research. This is not application oriented. This is more like some fundamental research or fundamental areas that people are beginning to explore. So there's a lot of interest in 2D and 1D electronic materials, and there's been a lot of developments that have happened over the last couple decades in this. Traditionally, electronics were made from 3-dimensional materials, meaning like it's like a box, right? 3 dimensions. Now, as we continue to miniaturize, we're starting to move towards 2D and 1D materials. So what is a 2D material? Well, it's a material that's a single layer of atoms. Single layer of atoms. Okay, you might think, well, geez, something that's just a single layer, can that actually even work in terms of conducting electricity? And the answer is yes. It turns out that in fact it's quite a good conductor. So this 2D material is called graphene. It's made up of a 2-dimensional sheet of carbon atoms, and they form like rings like this. We'll talk about this more in the next module, like what these atomic structures are. And if you take one of these sheets and then you roll it up into something like this, like a roll, now you have something that's almost 1-dimensional. Okay, it's just a single ring of carbon atoms if you look at the cross section. So this is called something called a carbon nanotube. All right, so both of these materials turn out they have like unique electronic properties that are that you typically don't see in 3D materials. And one of the things in particular is high mobility. High mobility means the electrons or charges can move very rapidly through the material. They can shoot through the material pretty quickly because they're not bumping into other things as much. This is true of graphene, 2D, and it's also true of carbon nanotubes, which is like where electron transport happens just along the electrons go right through the middle of this nanotube. The other unique properties is that they can conduct electricity on only a single direction. For example, the carbon nanotube like only conducts electricity in this vertical direction, and 2 dimensions in the case of graphene. There's a lot of applications of these types of electronic materials, and people are actively researching what they call like 2D and 1D electronic materials. Applications in computation, high density storage, environmental sensing, and even energy storage. So just to jump in a little bit of the specifics of this, there's always a question of how can we make better transistors, right? Because you saw this slide on Moore's law, you know that the fundamental transistor is like really important. So we're always trying to make the transistors better performance, and the material scientists in the area are always looking at like, well, what kind of materials could we use to improve the performance of transistors? So for many years, it's always been silicon, and the mainstream stuff is still silicon, just because the whole industries has been built around silicon. But there are materials, other materials. I mentioned graphene, molybdenum disulfide, bismuth, selenium, tungsten, selenium. These are all examples of some materials that that researchers are looking at. The reason they're looking at them is they can potentially provide lower power consumption. They may have higher mobility, so that can give you faster clock speeds, lower resistances, potentially lower cost and mechanical flexibility. For example, graphene is a flexible, transparent conducting material, mostly conducting. So this is what a conventional MOS transistor looks like. Some of the 2D electronic material transistors look more like this. A single layer transistor has literally a single layer of atoms between the source and the drain, and that's basically the farthest you can go with traditional transistor designs. Okay, so for the material scientists, like in the class, when you study electronics, you basically look at some fundamental electronic properties of the materials, and then you also look at the performance of the transistors that are made using the materials. And so some of the fundamental material properties would be things like band gap. Band gap tells you like if it's conducting or semiconducting. And then the mobility on the y-axis here is how fast the electrons move through the material. So that tells you how resistive it is. In general, higher mobility is better. So you can see graphene up here. In terms of band gap, if you don't have a band gap at all, then you don't have a semiconductor. So that's one of the issues with graphene. But on the other hand, too large a band gap, it'll be very non-conductive. So that's kind of some of the trade-offs that we face here. In terms of transistors, like you look at things like the on-off ratio, the current on-off ratio. We'll go into more of the details of that later. So you can compare materials in some of these two-dimensional maps. This is a kind of an interesting paper that was published in 2019, just a couple of years ago. Many groups are trying to push Moore's law and try to make the transistors at the atomic scale, at the nanoscale, and there are many challenges to doing that. But the ultimate limit is when you can make a transistor that is really a single electron transistor, meaning the transistor works by pushing a single electron through the material. At that point, that's pretty much the smallest we can do. That's a huge, challenging and ambitious problem to work on. And so one of the approaches that some researchers at MIT have done is to use carbon nanotubes to do so. Carbon nanotubes are these guys here, the ones where I said the electron flows through in one dimension. It's about the smallest wire you could possibly make. So they're trying to make transistors out of these carbon nanotubes. And turns out one of the tricks they use to do that is to actually have multiple nanotubes kind of in parallel. That way, if one of the nanotubes fails, then the other ones can kind of make up for it. And it also reduces the resistance to have multiple nanotubes in parallel like this. Now this schematic looks really cool, and it's like it says, well, you could build something like this, but a lot of times it happens that in research we tried to build one device, and it kind of works. You get a measurement, you publish a nice paper out of it, but actually making something with billions of or thousands of transistors on a chip cannot be done. So one of the things that the researchers here did is that they came up with manufacturing technologies that allows you to make these carbon nanotube transistors with some level of reliability. And so, I won't go into all the details of these, but they basically came up with different innovations to remove nanotube bundles and just have individual nanotubes. Impurities can often be a problem. So sometimes you have, when you make nanotubes, you make them using a chemical process, and not all of the nanotubes are semiconducting. Some of them are metallic, some of them not. So they had ways of designing logic gates that can tolerate that. And then the other thing is you need to have N-type and P-type. We haven't talked much about doping yet, but you need to have N-type and P-type semiconductor in order to make transistors. So they figured out some ways to make and pattern P-type and N-type carbon nanotubes. Okay, so what they were able to demonstrate is that they were actually able to make a microprocessor out of carbon nanotubes. So if this technology actually continues to become more robust and successful, we may see these types of computers in probably initially in niche applications, but then possibly in mainstream applications if a lot of the problems can be solved. Jumping to another area of that we're probably going to see a lot of growth in is the area of printed electronics. Yeah, let me just take a drink of water. Let's stop for a second. Any questions that we have so far? I know I'm covering a lot of very broad strokes of different material today. That's intentional. No questions? Okay. So printed electronics. If you imagine if we could print electronics very much like how they make newspapers, using like roll-to-roll processes, the cost of electronics would become really dirt cheap. Another way to think about it is if you could imagine like taking your inkjet printer and using semiconductor inks to basically print out electronics from your inkjet printer. Think about how inexpensive that would be. That's one of the directions that we want things to go, that researchers are looking towards. Some of the important things are like making flexible displays out of printed electronics, and then making things like solar cells out of printed electronics, because solar energy is like a very cost-sensitive application. Making a flexible printed electronics for clothing, for different types of sensors, for energy storage elements, for like automotive or other areas of more biomedical sensing. What these things have in common is that all the applications have some level of cost sensitivity to it. If we can make these electronics very cheaply and mass manufacture them, then it would really make electronics even much more ubiquitous than it is right now. So how do you make something cheap? Well, you have to have a cheap and quick manufacturing process. Traditional semiconductor devices are made from these solid crystalline materials. We're going to talk about this in the next module, how they're made, but they're made using these melt. You have to start from a single crystal melt and you form this thing called an ingot. It has to be done under very controlled circumstances because you want the semiconductor material to have pure crystalline structures. So naturally, it takes a long time. It's expensive. Compare that to if you were able to take like inks or semiconductor inks and basically print them out using a printer. So that's kind of where this field is going. So I have some links to some review papers in this area if anyone's interested in knowing more about this. Here's an image from some of those papers. And you can see how some of these inks, these semiconductor inks are made using roll-to-roll processes. Yeah, this is a gravure roller where you have a pattern that's embedded into a rotating metal wheel. This picks up the ink from one side. You have a squeegee blade here, and then it transfers that ink to the printing substrate. Things like that. Basically, like you have a printing substrate that goes through the machine and out comes the substrate that's been printed with electronic materials. And these are different ways of doing that. Okay, so for a solar cell, for example, you'd have to print on a P layer and then an N layer, because you need to have a PN junction in order to make a solar cell. Okay. And one area that's very close to me, an area where semiconductors are playing an important role, is in wearable health monitoring technologies. So how many of you own a Fitbit or an Apple Watch? Clayton does, yeah. Corey? Some of you, yeah. I have my Fitbit here. I'm actually working on a wearable tech. I'll tell you about that in a second. So, as you know, wearable technologies, some of the devices are just strictly activity trackers. Clayton, did you have a question, or are you just responding to my question?
I'm just responding.
Okay. So some of these wearable health monitoring technologies are just activity trackers. They're tracking the number of steps. There are some that monitor your sleep, some that monitor the waves, like brain waves during meditation or something like that. For diabetics, there's continuous glucose monitors that have sensors for sensing blood glucose levels. Things like the Apple Watch and the Aura Ring and the Zephyr bioharness. These are devices that you can wear on your body to detect heart rate, skin temperature, and activity levels. So they're multifunctional. Some of these devices are going to miniaturizing to the point where you can have something called electronic skin. I think this is pretty interesting. This is being pioneered by some really cool work out of UIUC, John Rogers' group there. They use like very thin electronics printed on flexible substrates, kind of like, I don't think they're using like totally printed electronics, but they're using like, thin flexible substrates, and they're putting, I would say, like thin electronic materials on them. They have different types of fabrication technologies that they use, but they make these things so thin that they call them tattoos. These are literally look like tattoos or little patches that you put on your skin. And some of the areas that they want to use this for is for like precise biological sensing of like chemical analytes and things that are going through your sweat or your skin. I think one of their things that they imagined was if you could have a bandage. You see how this kind of looks like a bandage? Like if you had a bandage that could actually monitor the how your wound is healing. They have something like that. They have a company that's commercializing some of this stuff right now. This is another example of a watch that does skin temperature, heart rate, and it does this electrodermal thing, which is also pretty cool. It can sense your level of perspiration, and from that, get an idea of how stressed you are. Which is quite interesting. There's also other types of perspiration monitors being commercialized right now for professional sports teams and sweat biomedical sensing. There's a company called Acrine Systems that's trying to look at different things in your sweat, like lactate levels. As you sweat out, it would be able to tell you physiologically about what your health status is. So it's one step beyond like just like looking at someone's heart rate. It's actually looking at levels of analytes in your skin, which is quite amazing. I think that's going to be the next step in wearable technology. So semiconductors plays a very important role in this. If you look at some of the devices here, you'll see that they have photo detectors and LEDs built into them. They have semiconductors are then used for the wireless radios to connect through Bluetooth. They're used in the power components so that the things can charge. All these devices pretty much are some type of Bluetooth wireless or some other wireless technology. All relies on semiconductors. So semiconductors in some cases can also be used for the actual sensing. Some of them use electrochemical sensors, some of them happen to be based on semiconductors. So a very important role for semiconductors in the future of health monitoring. All right, so good. We actually finished on time here. So to summarize, where we are at right now is that we are living in a day where semiconductors plays an incredibly important role. Everything from from the moment we wake up in the morning to the point we go to sleep, and even during sleep, as I pointed out, like some of these monitor you during sleep. So we're interacting with semiconductors pretty much all the time in the area of digital electronics, analog electronics, data storage and memory, various types of sensors, power devices for generating power and managing power, lighting, and then also like display technologies, like how much time do we spend staring at our cell phones and TVs and things like that. So they're all based on semiconductors. I hope that by learning the fundamentals in this class, you can actually explain how some of these things work to your peers, your family, your friends, and also for your own satisfaction as well. So we touched on some of the topics here in the class today. Some of the emerging topics, I hope that it may give you some inspiration or some ideas for your course projects, like what areas you'd like to explore further. Since this is a graduate level course, I would like you to think about which of these areas, and it doesn't have to be an area on this list, by the way. It can be any area that's of interest to you that's related to semiconductors that you would like to explore further and build your resume on. Maybe you want to understand it better if you want to like work in a certain industry. So that is your opportunity to explore further in an area of interest and tailor the class according to your own needs. But what I've done here is just give you an overview of the layout of the land. Starting next time in class, we are on Wednesday, we're going to start with the basic fundamentals of the crystal structures of electronic materials. So what does the atomic structures look like? And from there, we are then going to go to, well, how does the atomic structure then determine the electronic properties of the material? Okay, so that's going to be what Wednesday's class is all about. I think we'll end here today. Are there any questions that you have before we end today's lecture? Okay. All right, no questions it seems. Well, just a reminder then is that Wednesday, we will go into crystal structures in electronic materials. And September 15th, a week from Wednesday, is when the team selections. I would like you to have your teams selected. Now, it seems like we have like 5 folks in this class, so we'll have like one group of 3 and another group of 2. So, you know, you have a little bit of an idea of what folks' interests are. We introduced each other in the first class. Now you have a sense of what, you know, just a taste of what the different areas could be. Like I said, your project doesn't necessarily have to be on one of the areas that we covered here. In fact, maybe it's better if you just, you know, find an area that's of interest to you. And so in the next 10 days, I would like you to just find out if there's other folks in the class that have similar interests. Perhaps you can work on a project together. There's only going to be 2 teams really. So it's good you find people that you're interested in working with and have some common interests in terms of a project topic. Okay, no other homework today. Some of the homeworks and the mini quizzes that we're going to have online will probably start Wednesday or early next week. All right. So thanks everyone. Yep. Thanks Clayton and Corey, Prakash, Janan. I have to make sure I'm pronouncing your name correctly. Is it Janan?
Yeah, you see it correctly.
Okay, great. And Ali. So I'll see you all on Wednesday in class. We'll start with Module 1, Crystal Structures and Electronic Materials. If anyone wants to stay after class, I'll just stick around if anyone has any questions, because our office hours are after class. If I don't have anyone staying on, then that's fine. I'll just end the office hours, and I'll see you on Wednesday.
Thank you. Good night, Professor.
All right.
All right,
thanks,
good night.
Professor.
Good night, everybody.